Hello, we will continue in the same lesson, but now the part of area that is the title of the lesson. The first in an introduction, this video is to understand what is the concept that we will apply. Now here we have the Euclidean geometry. It says that we may find areas of square, parallelograms, triangle, etc. All the things that you study in geometry in a very easy way because we have formulas. But at the beginning, to find the area of the circle or to establish the value of pi was difficult, and the method that Archimedes used was by exhaustion. That means finding the area of the inscribed polygon and finding the area of circumscribed polygon. That means a polygon inside and a polygon outside, and depending on how many sides we have, the precision will be better. Let's see one example like this. This is the, the Archimedes method. We have an inscribed polygon here. We have a circle of 5 units with 5 units of the radius. I mean, from here to here we have 5. Remember how we find the area of a circle is the pi times the radius to the second power. That means will be 5 to the second power 25 times pi is 78.54. Now the area of this polygon that is inside here is the area of this polygon is 32.48. You see is a lot of difference between the area of the circle with the formula and the area of the inscribed polygon. Now 32.48, that means the precision that we have, the error that we have is 58.65. That is basically the half of the precision. But what happens if we increase the size? 4, now going to 5. Okay, now the area, the error of the difference that we have is only 24.32, only adding 5 sides to the polygon. It's a regular polygon, it's a pentagon. Now the area of the pentagon is 59.44, but the area of the circle is 78.54. It will be constant, this area, because we are not changing the circle. Now let's increase more this. Going to 10. You see how it's changing? It now is 6.45. When we have 10 decagon, that means we have a lot of sides. The precision is better. The margin of error is 6.45. Let's go with more sides. 20. 20. Now, see, basically the shape looks very similar to a circle, but it's not a circle. The area of this polygon is 77.25. It's very close to 78.54, and the margin of error is 6.64. If we go increasing and increasing and increasing, it's obvious that we are approaching, the idea is that the limit is approaching to infinity, but to calculate we can use it, but with 50 degrees, with 50 sides, sorry, a polygon with 50 sides, the margin of error is 0.26, is very similar. But if we are going to approach to infinity many sides, we will have the precision because the circle is a polygon with infinity sides, many sides. Now, the method that was for to find the pi, we find the diameter, etc., and then we divide. Remember, we need the circumference. Pi is the area is equal to pi times the radius to a second power. When we have the radius, only we have to divide the area that we have, we will have the value of pi. Now, this value that is the inscribed triangle here, and the circumscribed is the outside. See, it's a very huge difference. Inside is 2.59, outside is 5.19. And we know that pi is 3.14 with a lot of decimals. Now, if we continue increasing, it's approaching to number 3. Approaching, more, getting close, more sides, getting close to 3.14, 3.14 both sides, Here we have. It's approximation. In many sides we get this value. Now, that is the idea we will apply to find areas here. Why? We will make a figure similar to this. In the book, here it is. The area inside or below of a curve. That means the curve that make a function. If we make rectangles inside, similar to make polygon in different sections, we will get approximation of the area in the below the graph. But the rectangle can be less than the altitude has to be less than the function. I mean, the maximum is the function, or can be greater than the function. That means maximum. That means this approximation will give us a result that is it will give you a higher value than the real value of the function, but this one will give you a small value because we have spots here and we have extra things in this part. Now let's see in action. Maybe you can notice here we have the sigma notation, but later I will explain that. Now let's use this function x. The function is x. We know that is the intercept is 0. Now this is the shape. That means when the value of x is 10, the y is 10. Here we have. If we are looking for the area that is below the graph from 0 to 10, we will have a triangle. The triangle is going in this part. All this part will be a triangle. Now we know that the base of this one is 10, and the altitude of this is also 10. We can see it here. We know the area of a triangle that is base and height divided by 2. Base 10 times the height 10, 100 divided by 2 is 50. We know by the formula the area in this part is 50. But what happens if we use approximation to find this one lower here? I mean a rectangle that is below. Here we have two rectangles. One rectangle, and here another rectangle. This part is the maximum of the rectangle. If we continue increasing this, here we have the area. We know that we'll go close to 50 because we know the area of this triangle is 50. If we continue increasing, getting close, more rectangle, sorry, more rectangle, you're getting very close to 50. Now, how is the base? What is the base of this rectangle? Is delta x. That means the change in x. Here can be 9.5. Here is 10. That means it's 0.5. But if we continue increasing, this base of the rectangle will be approaching to 0. Remember the limit class? Now we have what happens when we have a maximum. Let's see it in this way. See, the base is, let's make this one the maximum. The corner is in this part. If we continue increasing, 100 is more than 50 because the max is a maximum. Here we continue, we get 51. In the other was 49, and this one is 50 because it's in the middle of the function. Now with a linear function, it's kind of silly to make this because we have formula. But what happens when we have a shape like this? Now we have this x second power plus 2. This is the function that we have. This is the graph, parabola. If we are looking the area below of the graph that is between 1 to number 4. This is not a triangle. This is not a parallelogram or trapezoid. No. This is a different shape because this is not a linear function, this part. Now, what happens if we start giving values to the rectangle? Here we have two things. The rectangle that is the maximum and the above, and the rectangle that are below of the graph. Here we have the difference, right? The maximum and the minimum. If we continue increasing the quantity of rectangles, See, the difference is getting small. That means the precision of the area, it is increasing, the value of the area, it is increasing, if we are continuing increasing the quantities or rectangles that we have here. Now the difference is only 0.445, and with the rectangles that are above is 27.22, and the rectangles that are below is 26.77. That means the real value is between those numbers. It will be a good decimal, then later we will find that value. But now I want to be clear that if we continue increasing the quantity of rectangles, the precision is better. It's getting close to the real value that is the topic. Now, you see it. Here we have the addition of rectangles and the areas. I will explain this in the next video with some exercise to solve.